Hello, my name is Mirjam Borger, and today I will tell you about my research on estimating fitness from empirical data. As you all know, measuring fitness in the wild is difficult. Often we use proxies for example, survival, body size for quality, for example, or proxies for fecundity, number of offspring or number of offspring that you actually see back in the next year. But as you all know, this isn't really a good estimate for fitness because optimizing survival or fecundity is not necessarily optimizing fitness, as there is a trade-off between them. And therefore, we often try to estimate lifetime reproductive success, as this includes that trade-off. Now, lifetime reproductive success is the number of offspring an individual produces over its entire lifespan. And typically, Altenbroek added that these offspring need to come back, but that doesn't really matter for now. Because lifetime reproductive success is still actually a problematic estimate for fitness, because it assumes that every offspring is worth the same to parents in terms of evolutionary value, while this doesn't necessarily have to be true. So for example, in a population with skewed sex ratios, for example, here there is 3 times more females than males, which means that on average, every male has 3 times higher fitness than every female. And because every individual has one father and one mother. And therefore, producing a son might actually be a much higher fitness benefit for parents than producing a daughter, because these sons on average also can spread the genes of these parents a lot more efficient than daughters can. And to solve this and other problems with lifetime reproductive success, Fisher came up with the reproductive value. Reproductive value was defined as the expected contribution to the future gene pool of an individual of a certain class. And reproductive value is so useful because it does exactly that, what I just discussed. It kind of gives a value to each group or class of offspring. And with that, you can estimate a sort of lifetime reproductive success that then takes into account these weighs per group. So for example, in the previous example, it could weigh every son 3 times as more as every daughter, and therefore give a much better estimate of what fitness really is. Now then the next problem is, of course, that these reproductive values need to be estimated in the wild. And traditionally this was done with a whole lot of complicated mathematics. The mathematical definition of reproductive value was always something like the fecundity you have right now multiplied by the fitness that these offspring will give you in the future, plus your expected survival, so your survival probability, multiplied by the fitness you'll get in the future if you manage to survive to that point. And you can estimate fitness using these complicated methods by estimating these fecundity and survival parameters. So you basically make a life history model, and you decide what the important categories are. So in this case, there's age, but you can add anything like dominant status or sex or whatever is important. And then you can estimate fitness from that. However, if you do add things like sex or dominance or whatever, this mathematics can become really complex quite easily. And therefore it was great that not that long ago, a new method to estimate reproductive value was introduced, where they used pedigrees. And this method intuitively makes sense because it's really close to the definition of Fisher's reproductive value, because what they do is don't look at the expected contribution, but at the actual contribution to future populations of an individual. So what they do is make a pedigree, and then they look at the population that's living right now, and then look at their genes and see from who they have descended. And then they can calculate or they can estimate reproductive value of these ancestors. However, both of these methods actually have never really been tested on how well they can estimate fitness. So the question for my research is, how precise and accurate are this pedigree reproductive value and the model-based reproductive value methods in really estimating fitness? Now, of course, answering this question is only possible in simulations, because that's where you are inputting the data, and therefore you know what the true fitness is. So that's what we did. We made simulations where we always started with 1,000 individuals, and all these 1,000 individuals, we gave them a gene, and their offspring would inherit this gene. And because of that, on every time step, we could see how many descendants there were from each individual. Next to that, we started the simulation in demographic equilibrium. And then we, at every time step, we first let individuals reproduce. So we plugged in expected fecundities. And then from a Poisson distribution with these expected fecundities as a mean, we drew the actual reproduction of individuals. And then next up, we checked if they would survive or not. So again, we had an expected survival probability, but then from a binomial distribution, we would draw if they would survive or not. We used density dependence in the population to assure a more or less stable population size, because we didn't want the population to go extinct or to grow exponentially, as that's not really biologically relevant. And of course, with simulations, you always want to do replicates to make sure that the pattern you're finding is really general. So we did 100 replicates of every simulation. And in each simulation, we estimated the model-based reproductive value by looking at these real fecundities and survival probabilities of individuals, and with that calculated their fitness, estimated their fitness, and we counted the descendants per individual to estimate this pedigree-based reproductive value. So on to the results. To compare these estimates with the true reproductive value, we set the reproductive value of the first group to 1. And since fitness is relative, this is not a problem. And then looked if the reproductive value of the second age group, in this case, was estimated well or not by both methods. So in this case, the true fitness was for the second group was 2, the true reproductive value, and so the model-based reproductive value estimate this really well. However, the pedigree-based reproductive value did something completely different and didn't estimate the reproductive value correctly. So of course we did this for multiple simulations, and so here in the top row you can see 3 example simulations for this 2-stage model, and in the bottom row you can see 3 example simulations for a 3-stage life history model. And what you can see is that sometimes the pedigree reproductive value underestimates the true reproductive value, sometimes it overestimates it, sometimes it actually does estimate it correctly, but the model-based reproductive value always consequently estimates it correctly. And to show that we are cherry picking in this, we also summarized all our 100 simulations, but then we summed up the total of all reproductive values to 1 to see where the variance really was coming from. So in this case, you see here the fitness of the reproductive value of 1-year-olds and that of 2-year-olds. And what you see is that the method-based reproductive value always represents the correct value well. There is a little bit of variation between simulations, but not really. However, the pedigree reproductive value shows a lot of variation and really doesn't estimate the reproductive value that well. And again, remember that one simulation is what would happen in the field, basically. So if you would use the model-based reproductive value, then you would get a correct estimate. However, if you would use the pedigree method, then there is a big chance that you might not add up at the correct estimate. And then there's another problem with the pedigree-based model that I'll show you as a summary of these 3-stage simulations. So here you see a summary of these 100 simulations again, where the dots connected by the red line are the median values of these 100 simulations. The dark shades are the 50% inner values of these simulations, and the light shade are the 90% inner values. And what you see is that in the beginning, all these simulations are kind of agree on doing the same thing. However, they show this sort of zigzag pattern. So in the beginning, they all do the same, but they're not accurate. While in the end, well, on average, these simulations get to the right estimate. However, there is a lot of variation between them. So in summary, the pedigree reproductive value is not a good estimate of the reproductive value. It has very low precision, so stochasticity has a big impact on its estimate, and there is a systematic bias in the beginning. I didn't really show this, but when these simulations become more realistic and more complex, this actually makes the estimate worse in general. The method-based reproductive value can be a good estimate of reproductive value. It has high accuracy and high precision. However, but this also actually is a point for the pedigree reproductive value. You need to have the correct life history model. So if you don't add in the correct important life history traits, then your model could still be useless. So finally, I of course did this together with my supervisors, Franz, Jan, and David, and I am finishing my PhD in half a year. So if you would like to collaborate in the future, or if you have any other questions, then feel free to email me. Thank you very much for your attention.